So let F be a field. Then an extension of F, is a field E, right? Is a field E such that F is contained in E and is a subfield. Clear? We denote in this case it as E bar. Okay, fine. For example, immediate examples is that C over R over Q. This is an example of a field extension. In fact, it's an example of a chain of field extensions, right? Something which you can observe from here immediately, that if such an occurrence you have, that is F, F extends to E, and F is an extension of, let's say, K, then E is also an extension of K, right? This is very easy to observe. Now observe the following, that if E is a field extension of F, then E is a F vector space, right? E is a F vector space. It is pretty easy to notice, right? Because first of all, the additive operation is nothing to be very concerned about. But if I choose alpha from F and I choose X from E, then alpha times X should be in E by closure, right? Because alpha in F and F is contained in E. So alpha times X is in E by closure of multiplication, right? Because E is a field, right? So there's a well-defined multiplication and a well-defined addition. So E is a F vector space. And if E is a F vector space, then I can talk about the dimension of E as a F vector space. And this is something which we denote in this way, right? And this is called the degree of the extension E by F. Clear? Example, that C over R is a degree 2 extension, right? Because you can clearly observe that if I choose an element Z from C, then Z can be written as A plus IB, right? So therefore, you can immediately observe it, and if you have studied vector spaces, then it is also a very trivial observation that the basis of C is so the basis of C is 1I over R, right? Because every element is essentially a linear combination of 1 and I, while the scalars are coming from R. So it's a pretty trivial observation. So it's a degree 2 extension. Is it clear? Okay. Number one. Number two is that R over Q is an infinite extension. Yeah. Okay. And a simple reason to say it is the following: that is, Q is countable, right? This is something we know, that Q is countable, while R is uncountable. Right? While R is uncountable. Is it clear? So if this would have been a finite extension, what does it? Why is it this fact necessary to say that R over Q is an infinite extension? Because if this was a finite extension, then we would get a basis, say E1, E2 till En in R, so that every element X can be written as some A1 times E1 and so on till An times En, where each AI comes from Q, right? But since Q is countable, so the choices for each of these AIs is countable. This basis is fixed. Therefore, the number of possible elements of this form is countable, which would prove that R is countable, right? Which would mean that R is countable. Is it clear? Got my argument? That is, each of these AIs have only countable number of possibilities. So a linear combination of a countable number of possibilities is still a countable number of possibilities. So there can be countably many elements of R. But that is a contradiction to the fact that R is uncountable. Is it clear? Is it clear for everyone? Fine. Right. Okay. So therefore, R over Q is an infinite extension. Fine. Now there is also a very interesting sort of a field which we call the field of Gaussian numbers. Okay. So this is defined as the collection of elements of the form A plus IB such that A and B comes from Q. Okay. This is called the field of Gaussian numbers. Okay. You can immediately observe that Qi is a field extension of Q, right? And in fact, the degree of extension is 2. Because every element is a linear combination of of 1 and I, where the coefficients come from Q, can be easily observed from here. And 1 and I are obviously linearly independent. That is not a matter of fact to observe from the comparison or the equality of complex numbers in any case. For example, Ri is basically C. Okay, if you define Ri in the same way as we define Qi, right? Okay. An interesting example is the following. If you observe f of x, what is this basically? This is the fraction field. This is the fraction field of fx. That is the collection of all polynomials px over qx, such that px and qx come from fx, and qx is non-zero for all x. Is it clear? Then this is a then this is basically infinite extension over f. Okay, is it clear? Fine. Right. So I'm going a bit slow because I want you guys to observe. In the later part of the lecture or in the later lectures, I'll become a bit fast. Okay. So this is the first lecture. That's why I'm going through a bit slow. Now you can observe something from here. If you have studied vector spaces, then you can relate it to whatever I'm going to say now. Let's move on to the next page and observe this proposition and try to relate the theory of vector spaces here. I think you guys can easily do that. Okay. Let L be an extension of E, E be an extension of F. Okay. Then L over F is of finite degree if and only if L over E and E over F are of finite degree, and in this case the degree of extension of L over F is the degree of extension of L over E times the degree of extension of E over F. Okay, you can relate it to vector spaces or you can relate it to cardinality of groups, but this is in some sense this is a very general theory of abstract algebraic structures. Okay, fine. Yeah, let's see the proof, and the proof is actually very simple. If you have studied vector spaces, then it's actually very simple to observe the proof. See, if L over F is finite, then it is clearly observable then that L over E is also finite, right? It is obvious. And since E is a subspace of a finite dimensional F vector space, so E over F is also finite, right? This is a very easy observation. Okay. Now let L over E and E over F be finite. What do we want to prove? To prove that L over F is finite. Okay. Let us do one thing. Okay. Let us do some basis elements. Okay. Let EI, let's say I is equals to 1 to M, be an F basis for E, and let's say LJ, J is equals to 1 to let's say N, be an E basis for L. Okay, we can do this now. Okay, so what we need to show? We need to show that L over F is a finite dimensional vector space. Therefore, if I am able to construct a basis of L as a F vector space, then we are good to go. Right? Right. Now, let us do something. Let lambda be in L. Okay. So if lambda is in L and L is L over L, I mean L over E is a finite dimensional vector space, Lj is a basis. So that implies that lambda can be written as summation Aj Lj, right? J is equals to 1 to 1, right? Fine. But then observe now that Aj, now where Aj, this Aj comes from, so Aj comes from E, right? Aj comes from E. So if Aj comes from E, then that implies that I can write Aj as summation, let's say Bij Ei. I is equals to 1 to, right? Where these Bij's come from F, right? Easy to observe. So what does this give us? So this implies that I can write this element gamma as summation over I and j of Bij Ei Lj, right? So I can take this as a whole as to get as a collection of elements where these Bij's come from F for all Ij. So this means that basically L is contained in the span of the elements of the form Ei Lj for I and j. Whatever index there, I'm not explicitly writing that anymore. And the converse is immediately true, right? Because each of these EIs and each of these LJs are in some sense in capital L, right? Because these EIs were chosen to be an F basis of E, right? Right. And E is contained in L, so each of these EIs must be in L as well. Each of these LJs are also in L. So EILJ is in L. So a linear combination of EILJs should also be in L. So this is trivial, right? So what we have proved, therefore, L is the of span of EILJ, right? I is equals to 1 to m as far as I remember, j is equals to 1 to n. Please verify. I forgot what was the range of the index I had chosen. Nevertheless, what we wanted to prove is that there exists some finite spanning set. Now observe the following. Now let summation aij ei lj be equal to 0. So this can be written as summation aij ei lj is equals to 0, right? Where was these aij's coming? These aij's were coming from f, right? Now what does this imply? Now therefore, since the LJs are linearly independent, this implies, so this is over I and j, right? So this implies that summation over I, aij, ei must be equal to 0 for all j, right? But then since ei's are linearly dependent, this implies that aij is equals to 0 for all I. What does that mean? Right? Getting my point? Right? Therefore, aij must be equal to 0 for all ij. Is it clear? Is it clear? Therefore, what have we concluded? Therefore, the collection EILJ over INJ is linearly independent and it spans, what does it span? It spans L over F, right? Therefore, what do I conclude? This implies that L over F is finite dimensional. And in fact, we have already proven this by the way we have constructed the basis that the dimension of L over F is equal to the dimension of L over E times the dimension of E over F. This follows from the construction of the basis of L over F, right? There might be some background noise, but please pardon me. I'm trying to record in as much peace as possible. Whatever. So I hope this part is clear, right? So what have we concluded yet of now is that if you're given a field, and so of extension of that field is basically another field which contains the starting field as a subfield, right? This is something which we have already concluded. Got my point? And then we talked about what we essentially call the dimension of a field, of a field extension, that is just the sort of a dimension of a vector space. Is it clear? Okay. Now let us talk about a very important thing. Okay. Let me think of something. Okay. Now let me define something. Okay. A field extension K over F is called an algebraic extension. Is called an algebraic. Okay. Let me first say what is an algebraic number. Okay. Now alpha in some field K, which is an extension of F, is called algebraic over F if there exists some polynomial Pt over F such that alpha is a 0 of this polynomial, such that P of alpha is equals to 0. Clear? Example, I in C as an extension over R is algebraic over R, right? Is algebraic over R as P of I is 0 where P of t is t square plus 1, right? Similarly, so it's example 1, example 2, root 2 in R as an extension over Q is algebraic over Q, is algebraic over Q. Clear? Now this is a well-known fact that pi in R as an extension over Q is not algebraic over Q, right? There exists no polynomial over Q whose root is 1. That is something, is a well-known fact of mathematics, right? Fine. So there might exist numbers which are algebraic over the subfield. There might not exist such a number. Okay. So when will I say that a number is transcendental? Such numbers are called transcendental, which are not algebraic. Okay. So definition: alpha in K as an extension over F is transcendental. Is transcendental if there does not exist some polynomial Pt over F such that P of alpha is 0. That is, there exists no polynomial over the subfield. Okay, whose root is alpha. Now, this is again a very trivial observation. If alpha is in F and I consider F as an extension of itself, because we know that every set is a subset of itself, so every field is a subfield of itself as well, by trivially from the definition, sort of a very tautological concept. So if alpha is in this, then observe that if I choose P of t as t minus alpha, this is a well defined polynomial over Ft, right? Because this is just 1 times t, so 1 is in F and alpha is also in F by our assumption, and P of alpha is 0. Therefore, every element in a field is algebraic over it. So to talk about transcendental numbers over an extension, we need to talk about only those numbers which are not in the underlying field, right? This is sort of very clear. Got it? Now, okay, another remarked definition which is more well known, that is alpha in C over Q is called an algebraic number. Is called an algebraic number if alpha is algebraic over Q. Fine. So this is sort of what should I say, a more conventional thing which came first. Okay. So algebraic elements in complex numbers treated as an extension of Q are basically called algebraic numbers. Okay, and otherwise a transcendental number. Otherwise transcendental number. Okay, so they are the same things in different aspects. Okay, transcendental number. If I talk about an element being algebraic, then it's a general theory talking over any general field extension. Algebraic numbers are specifically for complex extensions of Q. Okay, complex extension of Q, to be very specific. We'll see later that why I'm talking about it to be complex extension, because it will come out to be unique up to isomorphism. Rather, that's a notion for some different lecture. Whatever. Now let us come to the definition which I wanted to make previously. Definition: a field extension K over F is called an algebraic extension. Is called an algebraic extension if every element of K is algebraic over F. Is algebraic over F. Okay. If there exists some alpha in K such that alpha is not algebraic over F, there exists even one such element which is not algebraic over F, then K over F would be called a transcendental extension. Is called a transcendental extension. Clear? Okay. Some immediate examples. Example: C over R is algebraic extension, while R over Q is transcendental. Why? Because pi, there exists the element pi which is not algebraic over Q, right? Fine. So C over R is an algebraic extension. Can you prove it? Right. I think this is very easy to prove, that if you choose a complex number, then there always exists a real polynomial whose root is this complex number, right? Yeah, this is actually a very easy proof. So if alpha is in C, okay, let's say alpha is in C minus R, to be very specific, okay, then I can choose Pt to be t minus alpha times t minus alpha bar, right? Then clearly P of alpha must be 0. And if I expand it, what should I get? I get t square minus alpha plus alpha bar t plus alpha into alpha bar, right? This is equals to t square minus 2 times the real part of alpha times t plus mod of alpha square, right? But then this is a real number. This is also a real number. So this is over R, right? Right. Therefore, what do I conclude? That any element outside R in C is algebraic over R, and any element in R will automatically be algebraic over R. So this proves that C over R is an algebraic extension, right? While R over Q is a transcendental extension from the existence of point. That's quite obvious to observe. Is it clear? Fine. Fine. Now, a very important sort of an observation is the following: that there exists only countably many algebraic numbers. Recall, algebraic numbers are elements in the complex field which are algebraic over Q, right? And this is also, I won't say it's a very easy observation, but yeah, it's a sort of, you can see it in the following way. See, Q is countable, right? Q is countable. That means any finite direct product of Q, let's say QD, is countable, right? Now recall, the way we had constructed the notion of polynomials was actually from the viewpoint of direct product of fields, if you recall, right? We had chosen some n tuples, and then we had defined the polynomials to be isomorphic to those n tuples by mapping the coefficients of the polynomials to those n tuples. Recall, right? So this in fact implies that Qt is countable, right? A very easy observation. Now each polynomial has only finitely many roots. Each polynomial has only finitely many roots. Roots in complex numbers in general has only finitely many roots, right? And the collection of all these roots are only what we call the algebraic numbers, very specifically, right? Thus observe that therefore from the set of algebraic numbers, right, what do I have? We have a finite to one map. We have a finite to one map to Qt, right? Because there can be, say, four roots all going to the same polynomial, right? That by a finite to one map from algebraic numbers into Qt, and Qt is countable. So that, what does that mean? That means that the set of algebraic numbers is countable, right? So it isn't as large as it seems to be. The collection of algebraic numbers are not as large as it seems to be. Yeah. Okay. So I guess this part is fine, right? Okay. Yeah. So So what we have discussed? So we have discussed about algebraic extensions, finite extensions, and transcendental extensions as well, right? Okay. Let me think of something more at this point. Um, right. Yeah. So, oh sorry. Wait a sec. Right. Now observe the following. Okay. This is also very important to observe. Okay. Observe the following. Um, or rather, let me just give it as a theorem itself. That is, every finite extension is algebraic in nature. Okay. Every finite extension is algebraic in nature, and the proof is actually very simple. Let k over f be finite. Let k over f be a finite extension, and let alpha be in k. Okay. So what do I need to show that? I need to show that alpha is algebraic over f, right? From the definition of algebraic extension. Let the dimension of k as an f vector space be n. Fine. Now observe the following. Now, since alpha is in k and the dimension of k as a vector space over f is n, so 1 alpha square till alpha n is a collection of n plus 1 elements in k, right? N plus 1 elements in k, right? Is it clear? Therefore, the collection 1 alpha square till alpha to the power n is linearly dependent in k over f, right? Because we know that if I have a dimension, or rather if I am in a finite dimensional vector space, and there is a set of distinct elements, I mean rather a set containing elements more than the dimension, then that set must be linearly independent. Linearly dependent, right? Because the basis is basically the maximal linearly independent set, right? These are the terms we should know if you have studied vector spaces. In fact, even if you have studied vector spaces over an undergraduate course, right? So what does that mean? That means that there exists a0, a1 till an in f, not all 0, from the definition of linear independence over f, such that a0 times 1 plus a1 alpha, so on and so forth, till a in alpha to the power n is equal to 0, right? So let pt be the polynomial a0 plus a1t, so on and so forth till a n t to the power n. And since each of these ai's are coming from f, so this must be a polynomial over f. Then clearly p of alpha is 0. But what does that mean? That alpha is algebraic over f. And alpha was an element which was arbitrarily chosen from k. That means that this means that k over f is an algebraic extension. Is an algebraic extension. Okay, is it clear? Now I'm leaving this for now. I will talk about this later when we have developed some more theory. Okay, at least the theory of constructible numbers we require that a bit. Okay, uh, that is the converse is not true. Okay, I'll later give an example outside the notion of constructible numbers, because I'm not yet sure that whether we will talk about constructible numbers or not. If I do, then I'll give an insight when I will be talking about constructible numbers or not. But after I mean, I can do it in the next lecture itself. I'll give because we need a more mathematical maturity to understand that example. So I'm leaving it in this lecture because in this lecture we are only developing the basics. Okay, so converse is not true in general. In the meantime, you can try and surf to the internet to find out a counter example. Nevertheless, we will do that in the next lecture. Is it clear? Fine, right? Okay. Now, this is the one of the most important theories uh, one deals with in field theory is the following. Okay, let alpha be an element in K as an extension over F. Okay. Define F alpha to be the smallest, let's say smallest subfield, because we have already developed a field extension. So smallest subfield of K containing both F and alpha. Okay, continue. So F automatically becomes a subfield of F alpha as well. Okay, is it clear? So now our goal is to give a structure to F alpha. So our goal is to give a structureize F alpha. And let's see how we are able to do this. Okay, let's take a map phi alpha from Ft to K. And by the notation, I guess you should have already understood what this map is. This is the evaluation map of at alpha. So I'm writing this previously itself. So what we are working with is the evaluation map at alpha. So what is it doing? It is taking a polynomial ft and it is mapping it to f alpha. Clear? Okay. And clearly, phi alpha is a well-defined homomorphism. Is a well-defined homomorphism. What is the kernel of phi alpha? The kernel of phi alpha is the collection of all those polynomials pt in ft, qt in ft. We will see why I'm using the notation qt. That is not a matter of fact at all. You can use any notation, right? Such that q of alpha is 0. In other words, it is the collection of all those polynomials over f which has alpha as a 0 or alpha as a root, right? What is the range of phi alpha? The range of phi alpha is p alpha such that pt is a polynomial in ft. So let me denote it as f alpha. Okay. So this is basically the collection of elements of the form a0 plus a1 alpha, so on and so forth till a n alpha to the power n, such that n is a natural number and each ai comes from f. Yeah. Let me denote it as this. So in other words, this is the collection of all the values which we get on evaluating each of the polynomials at alpha, each of the polynomials over f at alpha. So now, having this well-defined homomorphism by the first isomorphism theorem of rings, what do I have? Ft mod kernel of phi alpha is isomorphic to our f alpha. Right? It's clear, right? Fine. Now comes the important thing to observe. See. Now, this kernel of phi alpha, we had proved this previously that the kernel is actually an ideal, if you recall. Okay. So it is typically an ideal of Ft. And f is a field, so the polynomial ring over a field is recalled a PID. Got it? It is a PID. Okay. Now, Yeah. Now see F or rather K is a field, right? K is a field, or let's say let us first so that means that kernel of phi alpha is actually generated by some polynomial pt. So pt comes from it, right? Now K is a field, that implies that f of alpha is an integral domain, right? What does this imply? This implies that uh, uh, ft over ideal generated by pt is an integral domain. What does this imply? Recall from the characterization of prime ideas, this implies that pt is a prime ideal. But recall then what does this imply? That pt is a prime element from the definition of prime elements. But then also recall that every prime element is an is okay rather yeah, so typically it's a prime element. In fact, it's an irreducible element. If you recall that every prime element is irreducible in nature, that implies pt is irreducible, irreducible over f. Is it clear? But then what more do I have? Over a PID, every non-zero prime ideal is a maximal ideal. This is obviously a non-zero prime ideal because I haven't chosen it previously, but alpha is obviously zero. What is the fact in choosing it to be zero? It's non-zero. I mean, alpha is non-zero. So every non-zero prime ideal is a maximal ideal. So this is one sort of an observation which we have. Other observation is that PT is maximal. Over a PID, we call over a PID every non-zero prime ideal is a maximal ideal. So what does this mean? This means that FT mod PT, what can I say about this? Is a field because PT is come out to be a maximal ideal. So what does this mean? This means that f of alpha is a field, right? F of alpha is a field. Is it clear? Is it clear for everyone? Right. Okay. Now this is also pretty trivial to observe that this PT, this irreducible polynomial of over Ft, this can actually be chosen to be monic. Okay, because we are working over a field. If it is not monic, recall that the ideal generated by u times some element v is same as the ideal generated by v where u is unit, right? So if pt is not monic, if not monic, right, then just take common the coefficients, okay, or rather take common the first element, not the coefficients, take common the first element, bring it outside, that gives you a monic polynomial. And since the first element is a non-zero constant, so that element is in a non-zero element in f, so that is a unit, so we're good to go, right? So even if it's non-monic, I can make it monic. So in other words, in general, I can talk about this to be a monic polynomial. So actually, we have proven two things. First, let me complete what my argument was. What I have proven is that f alpha is a field. Now observe, now f alpha is clearly inside this. Why is it so? Right? Why is it so? As since alpha is in f alpha and f is also is in f alpha, this implies all the elements of the form a0 plus a1 alpha, so on and so forth, a n alpha to the power n must be in f alpha by closure of addition and multiplication, right? On the other hand, we can easily observe that f alpha contains f and it also contains alpha, right? Right? Because I can choose every coefficient to be 0 and a1 to be 1, right? And I can choose every coefficient to be 0 and just leave except a0. So f is also in alpha as the collection of all constant polynomials evaluated at alpha, and alpha itself as the evaluation at the polynomial x or t, equal to t, f equal to t, whatever. So therefore, since it contains both of these, by definition of f round bracket alpha, it is the smallest subfield containing both f and alpha. So this means that this contains f. What do I conclude hence? Therefore, f alpha is same as f round bracket alpha. And this gives me a structure of the elements in f round bracket alpha from here. So this is the collection of all elements of the form a0 plus a1 alpha, an alpha to the power n, such that n is a natural number and each ai's come from f for all I. Yeah. And we have also proved that it's a field because we have proved this is a field, right? Is it clear? But we have proven something more here. We have proven this as well, that if I talk about an ideal I in ft, then I can always get hold of a, say with me, in this case where f is a a subfield of k, then I is generated by an irreducible monic polynomial. Monic polynomial. Is it clear for everyone? Right. Okay. Okay. Fine. Now also, I think this was not something to be mentioned, but I did it since you used it. I have also covered this in the previous lectures. But here I said now that every prime element is irreducible. I was specifically talking about in integral domains. Please make sure about that. Fine. Right. So this is clear. Clear for everyone. Right. So this F alpha is called the field generated by alpha. Clear? And the polynomial Pt, which is the irreducible monic polynomial such that P of alpha is 0, is called the minimal polynomial of alpha over f. Clear? I hope this is clear, right? Okay. Fine. Extensions generated by a single element are called simple extensions. Extensions generated by a single element is called a simple extension. In other words, if k over f is called a simple extension, if there exists some alpha in k such that k is equal to the field generated by f and alpha. Okay. Now once you have this definition in hand, then you can inductively define. I don't need to prove anything because you have already got every single structure of fields of this form. Inductively define f of, let's say, alpha 1, alpha 2 till alpha n as f of alpha 1 till alpha n minus 1 and generate it with alpha. Yeah. Is it clear? Fine. Okay. We are going good, right? The first day we have already covered a lot of things, a lot of important things. Is it clear? Now suppose, now consider the same map phi alpha from ft to k such that f of t is mapped to f of alpha, and so this is basically a homomorphism inside fields, right? Now the kernel of phi alpha is an ideal in a field, right? Right. So what are the or rather what I'm trying to say is the following. That, yeah. So yeah. So as I was saying that the kernel of phi alpha is either non-zero or zero. If it is non-zero, then we have already claimed a lot of things, right? And what have I actually proved? That if it is non-zero, then that means that alpha is actually algebraic over f, right? This is something which we have proved while doing the proof of the previous theorem itself, right? Because once the kernel is non-zero, then we would obviously get hold of a non-zero polynomial such that the polynomial takes alpha in as a root. But what if the kernel is zero? What if the kernel is zero? What do you conclude in that case? So the kernel is zero, that is, if the kernel of phi alpha is zero, that means that there exists no non-zero polynomial in k whose root is alpha. That means alpha is transcendental. So this is also a tool to check transcendental or algebraic nature of an element. So alpha is transcendental over f. And in that case, again by the isomorphism theorem itself, then ft is isomorphic to our definition f alpha, right? In this case, f alpha is defined to be the fraction field of f alpha, right? This is our notation for fraction field. Clear? Okay. Right. A simple collection of definitions now. Definition. Okay. So what we can conclude is that alpha in k as an extension over f is transcendental over f if and only if what do we have, f alpha is isomorphic to ft. Okay. This is the fraction field of f of t, which is the collection of all rational polynomials over f, right? Okay. And this is also an very easy, I mean, a definition. We say that alpha 1, collection of elements alpha 1 till alpha in k over f are algebraically independent if the fraction field of the multivariable collection of polynomials is equal to or isomorphic to this. Okay. If I have a field which is generated by a finite collection of polynomial, finite collection of elements, it is called a finitely generated extension. It's called a finitely generated extension. Okay. Is it clear for everyone? Fine. Right. Okay. Yeah. So let's now see what more can we do. Okay. Now, having defined a simple extension or an extension generated by an element, and also we have got hold of the notion of the degree of the minimal polynomial of that element, what we can conclude is the following. Let me give it as a theorem. So if alpha is in K over F, so let alpha be in K over F. If alpha is algebraic over F, then the degree of the extension F alpha over F is the degree of the minimal polynomial of alpha, where Pt is the minimal polynomial of alpha over F. And in some sense, this is why we call this, the dimension of K over F to be the degree of the extension, because it is in some sense related to the degree of some polynomial. Okay, provided that is algebraic, but that's now has become a conventional way. Okay, right. So let's try and prove it. And the proof is actually very simple. Proof. Okay, we already know that F alpha, since alpha is algebraic, so it's isomorphic to Ft over the ideal generated by Pt. Right, and this is this is actually isomorphic to F alpha. Right. So actually, what I have is that every element is in here is a linear combination of elements of the form. Uh, linear combination of powers of alpha. Right. Okay. Okay. Right. Let me not complicate what I'm trying to say. Let me do it in this way. Suppose Q of alpha is in F alpha. Okay. Where Qt comes from Ft. Okay. And let's say the degree of Qt is greater than the degree of Pt. Okay. Then by the Euclidean algorithm, what I can do, I can divide Qt by Pt. Then there exists, let's say Gt and Rt in Ft, such that I can write Qt as Ptgt plus Rt, such that the degree of R is less than the degree of P. Right? But then what do I have from here? From here I have that Qt is actually congruent to Rt in or rather in a simple notation is equal to Rt in Ft mod the ideal generated by Pt. Is it clear? Right. So what do I have? This implies that Q of alpha is actually equals to R of alpha in F alpha. Right. So therefore, now R can be any arbitrary polynomial with degree less than degree less than the degree of P. That implies 1 alpha square till alpha to the power n minus 1 spans Ft. Right. Right. So it's a very trivial observation, as we can see, and the linear independence of this is also very easy to observe. Okay, these are easily linearly independent, because if not, if a1 alpha till an let's say a minus 1 alpha to the power n minus 1 is equal to 0, then I can take hold of the polynomial qt, which is a0 till an minus 1 alpha to the power n minus 1, such that q of alpha is 0. But this contradicts the minimality of pt, because pt was the ideal which actually generated every element which contained alpha as a root. In other words, if you recall, because this is the kernel of phi alpha, what does this actually mean? This implies that if qt is such that q of alpha is 0, then that means that qt must be in the ideal generated by pt, which means pt would divide qt. Right? That's why the term minimal polynomial. It's a minimal element, right? Which has alpha as a 0. But if the degree of q is strictly less than the degree of p, then this contradicts this division. Clear? Therefore, this is not possible. So every ai must be 0. In other words, this collection is linearly independent, right? So what we have actually proved that f alpha over f is a degree p uh, dimensional vector space, right? Don't confuse it with the degree of R being or the highest power of each of these elements being less than n. Degree p dimensional vector space means the basis consists of n elements, and this collection 1 to alpha n minus 1 exactly contains n elements, right? This exactly contain n elements. I hope this is clear, right? Fine, right? Dimensional vector space with basis 1 alpha till alpha n minus 1, right? Where n is the degree of. Is it clear? An immediate example: q root 2 over q is a 2-degree extension. Why? As x square minus 2, p of x equal to x square minus 2 over qx is the minimal polynomial of root 2 over q, right? And the degree of p of x is 2. What should be the basis of this? 1 root 2. Okay. Okay. This brings us to the next definition. A field extension k over f is called a quadratic extension. It's called a quadratic extension if the degree of extension of k over f is 2. Okay. Yeah. So let's end this lecture here, and I'm giving you exercise. Please try it at home. K over f. Yeah. So my computer is lag. So let k over f be an extension. Then the degree of k over f is 1 if and only if k exactly equals f. Okay. Try this at home. Fine. Right. So meet you guys in the next lecture where we'll be talking further about fields. Thank you.